In this video, we're going to work on problems associated with specific heat capacity. The specific heat capacity for water is about 4.184 joules per gram per Celsius. So what does that mean? It means that if you have 1 gram of water, it requires 4.184 joules to heat that 1 gram sample by 1 degree Celsius. So specific heat capacity, it tells you how much energy you need to raise the temperature of a 1 gram sample by 1 degree Celsius. So a substance that has a very high heat capacity can absorb a lot of energy without changing its temperature much. A substance that has a very low specific heat capacity is probably a good conductor of heat. It only takes a small amount of energy to increase the temperature by a very large amount. For example, a metal. Most metals have a relatively low specific heat capacity. And as a result, when you add heat to a metal, the temperature rises quickly. So let's say if you put in a metal pot on a stove and there's nothing inside of it, it's an empty metal pot, you'll find that the temperature of the metal will increase rapidly. Whereas if you fill the pot with water, it's going to take a longer time to increase its temperature because water can absorb a lot of heat energy without increasing the temperature quickly compared to a metal. So water is very good at storing heat energy, and so it has a very high specific heat capacity. Now, if you want to calculate how much energy is absorbed or released when the temperature of a sample changes, you can use this equation. Q is equal to MCAT, or MC delta T. M is the mass in grams. C has the unit joules per gram per Celsius. And the temperature difference, or temperature change, is usually in Celsius. So notice that the unit Celsius cancels and grams cancel. So Q is the heat energy in joules. Delta T is the temperature difference. It's the final temperature minus the initial temperature. And you need to know some other unit conversions related to these problems. For example, 1 lowercase calorie is a unit of heat energy. It's equal to 4.184 joules. It's based on water. A capital calorie is 1,000 lowercase calories. And a kilocalorie is also 1,000 calories. So make sure you're aware of those unit conversions. So let's work on some problems. How much energy is required to heat 50 grams of water from 20 Celsius to 80 Celsius? And we have the specific heat capacity of water. The equation that we need is Q is equal to MC delta T. So the mass of water that we have is 50 grams. The heat capacity is 4.184 joules per gram per Celsius. And the temperature change is 80 minus 20. And the unit is degrees Celsius. So the answer is going to be in joules. So 80 minus 20 is 60 times 50 times 4.184. So you should get a value of 12,552 joules. Now let's say if you want the answer in kilojoules. How do you convert it from joules to kilojoules? All you need to do is divide it by 1,000. But if you want to set up the conversion factor, here's what you need to do. So start with the joules that you have. We know that 1 kilojoule is equal to 1,000 joules. So you want to write it in such a way that the unit joules cancel. So when you divide it by 1,000, it's the same as moving the decimal point 3 units to the left. So this is going to be 12.552 kilojoules. Let's try this one. 4,000 joules of heat energy is applied to a 70-gram sample of water initially at 35 degrees Celsius. What is the final temperature of the sample? So let's use the same equation. Q is equal to mc delta T. So this time we have the value of Q, and it's 4,000 joules. We have the mass, which is 70 grams. And we know the specific heat capacity of water, 4.184. And delta T is the final temperature minus the initial temperature, which is 35. So let's solve for the final temperature. So first, let's multiply 70 by 4.184. So that's going to equal 292.88. Next, let's divide both sides by 292.88. So 4,000 divided by that number will give you 13.6575. So once we divide both sides by this number, we no longer need the parentheses around TF minus 35. So it's simply TF minus 35. So now we got to add 35 to both sides. And this is going to give us the final temperature. So the final temperature is going to be 48.66 joules. I mean, not joules, but Celsius. So whenever you add heat to a sample, the temperature will go up. If you remove heat, the temperature will go down. So in this case, what we have here is an endothermic process. For an endothermic process, Q is going to be positive. If water absorbs energy, the temperature of the water sample will increase. Now for an exothermic process, where water is a system, Q is going to be negative. And that means water loses internal energy. And so the temperature of the water will decrease since it's releasing heat energy. Let's try this problem. It takes 30 calories of energy to heat a 13.2 gram sample of an unknown metal from 18 degrees Celsius to 49 degrees Celsius. Determine the specific heat capacity of the unknown metal. So the first thing we need to do is convert calories into joules, unless we want the specific heat capacity in units of calories per calories per gram per Celsius. Now, as we mentioned before, 1 lowercase calorie is equal to 4.184 joules. So we have 125.52 joules of heat energy. So now let's use the equation Q is equal to MCAT. So Q is 125.52. The mass is 13.2. We're looking for C. That's the specific heat capacity. And the change in temperature, final minus initial, 49 minus 18. That's equal to 31. So 31 times 13.2, that's 409.2 times the specific heat capacity. So now let's divide both sides by 409.2. So 125.52 divided by that number gives you a specific heat capacity of 0.3067. And the units is joules per gram per Celsius. Now, what is the difference between heat capacity and specific heat capacity? Heat capacity is calculated by taking the energy change, or the energy absorbed or released by a substance, and dividing it by the change in temperature that occurs. So heat capacity has units joules per Celsius or joules per Kelvin. The specific heat capacity, it's Q divided by M and delta T. So it has the units joules per gram per Celsius. The heat capacity depends not only on the identity of the substance but also on the mass of the sample. So for example, if you increase the mass of the sample, the heat capacity will increase as well. So therefore, heat capacity is an extensive property because it depends on the amount of material present. The specific heat capacity does not depend on the amount of material. If you increase the mass of the material, the specific heat capacity will remain the same. So for example, the specific heat capacity for water is 4.184 joules per gram per Celsius. Regardless if you have 10 grams of water or 20, the specific heat capacity for water will still be the same. Now let's say if the heat capacity for 10 grams of iron metal is, let's say, 5. The heat capacity for 20 grams of iron metal would be 10. It would double. Now we said that the specific heat capacity has the units joules per gram per Celsius. There's another one that you need to be familiar with, and that is the molar heat capacity. The molar heat capacity has units joules per mole per Celsius, or it could be joules per mole per Kelvin. So just pay attention to the units, and you can tell if you need to convert the unit from one unit to another. 100 grams of an unknown metal at 150 degrees Celsius was dropped in a bucket containing 50 grams of water, initially at 21 degrees Celsius. The final temperature of the mixture was 32 Celsius. What is the specific heat capacity of the unknown metal? So let's say if we have a container with water, and let's say we drop a metal inside of it. Initially, the temperature of the metal is 150 degrees Celsius, and the temperature of the water is 21 degrees Celsius. Heat flows from hot to cold. So heat energy is going to leave the metal and transfer to the water. So the temperature of the water is going to go up. It rises from 21 degrees Celsius to 32 degrees Celsius. So water is gaining energy. So thus, it's endothermic for the water sample. Now for the metal, it's going to lose energy. So therefore, the temperature of the metal is going to decrease from 150 to 32. So the process is exothermic for the metal. So this is a heat transfer problem. And let's assume that all of the heat energy lost by the metal is absorbed by the water. So with this information, how can we calculate the specific heat capacity of the metal? Whenever you're dealing with a heat transfer problem, you need to start with an equation that looks like this. QA is equal to negative QB. So the heat energy lost by one material equals the heat energy gained by the other material. Now, Q is negative whenever heat energy is lost, and when it's gained by a substance, Q is positive. So to make this equation work, you need to add a negative sign. It really doesn't matter which side you add the negative sign to, but as long as you have it, the equation will work. Because for an endothermic process, there's also an exothermic process. If iron metal, or in this case the unknown metal, if it loses heat, then something has to gain heat, in this case the water sample. So let's say QA is going to represent the metal. So QM is equal to negative QH2O. That's for the water sample. So it's going to be MC delta T is equal to negative MC delta T. So on the left side, the mass of the metal is 100 grams. We're looking for the specific heat capacity of the unknown metal. And the temperature change, it's final minus initial. The final temperature of the metal is 32 degrees Celsius, which is the same as the final temperature for water. Once these two attain the same final temperature, then there's no net heat flow. The temperature of the metal will continue to decrease to 32, and the temperature of the water will increase towards 32. Once these two are at the same temperature, at that point, the net exchange of heat flow will be the same, and thus the mixture will come to equilibrium once it reaches that final temperature. So the final temperature is the same for water and the metal. The initial temperature of the metal is 150 degrees Celsius. So notice that 32 minus 150 is a negative number. So thus we need the negative sign so that it cancels with this negative value on the left. On the right side, the mass of water is 50 grams. And the heat capacity of water is 4.184. And the temperature change, final minus initial, 32 minus 21. 32 minus 21 is 11. And if we multiply that by 50 and 4.184, this is going to equal 2301.2. But let's not forget about the negative sign. On the left side, 32 minus 150, that's a negative 118 times 100. That's equal to negative 11,800 times the specific heat capacity. So now let's solve for C. So let's divide both sides by negative 11,800. So the specific heat capacity of the unknown metal is 0.195 joules per gram per Celsius. A 100 gram sample of aluminum at 120 degrees Celsius and a 150 gram sample of iron metal at 90 degrees Celsius were placed in a container of 80 grams of water at 15 degrees Celsius. What is the final temperature of the mixture? So here we have another heat transfer problem. But in this case, there's three different substances. We have aluminum, iron metal, and water. So we have three different Q values. In the last example, we just had the unknown metal and water. So we had a QA and a QB. This time there's a QA, QB, and a QC. But we need to know how to set up the equation the appropriate way. So you need to know which substance is releasing heat energy and which one is absorbing heat energy. If you can understand that, then you'll know how to appropriately arrange the equations. So let's say if this is aluminum metal, and if we have iron metal. Now we know aluminum metal is at a temperature of 120 degrees Celsius, and iron metal is at 90 degrees Celsius, and the sample of water is at 15 degrees Celsius. So we know that heat flows from hot to cold. So heat energy is going to flow from the aluminum metal to the water sample, and it's also going to flow from iron metal to the water sample. So aluminum and iron, they're releasing heat energy. So it's exothermic for those two metals. Water is absorbing heat energy. So on the left side of the equation, we're going to put the substances that are releasing heat energy. So that's Q for aluminum, plus the Q for Fe, because they're both releasing energy. And on the right side, we're going to put the substances that are absorbing energy. In this case, only water absorbs energy. Now, we need to add the negative sign to either side of the equation. But let's add it to the right side. If you add it to the left side, you need to apply the negative sign to both Q for Al and Q for Fe. So now that we have the equation that we need, let's go ahead and calculate the final temperature of the mixture. So it's going to be mc delta T, that's for aluminum, plus another mc delta T for iron metal, and that's equal to negative mc delta T for water. So the mass of aluminum is 100, the heat capacity is 0.9, and the temperature change is final minus the initial temperature of aluminum, which is 120, and the mass for iron metal is 150. The heat capacity for iron metal is 0.45 times the temperature change, which is the final temperature minus the initial temperature of 90. And all of that is equal to, well, first let's simplify the left side of the equation since I'm running out of space. So 100 times 0.90 is 90 times the final temperature minus 120. And 150 times 0.45, that's 67.5 times the final temperature minus 120. So this is equal to the right side of the equation, negative mc delta T. So the mass of water is 80 grams. The heat capacity of water, that's 4.184 times the final temperature minus 15. So on the left side, let's distribute 90 to these two, and let's distribute 67.5 to those two values. And let's multiply 80 by 4.184. So 80 times 4.184, that's negative 334.72 multiplied by final temperature minus 15. So that's on the right side of the equation. So let's distribute the 90. It's going to be 90 times TF, and then minus 90 times negative 120, so that's negative 10,800, plus 67.5 TF, and then 67.5 times 120, that's negative 8,100, and all of that is equal to negative 334.72 TF, and negative 334.72 times negative 15, that's positive 5,020.8. So let's combine like terms on the left side. So 90 plus 67.5, that's 157.5 TF. And then let's combine negative 10,800 with negative 8,100. So that should be negative 18,900. And this is equal to what we have on the right side, which is negative 334.72 TF, plus 5,020.8. So let's add 18,900 to both sides. So if we do that, we're going to have this equation. So 5,020.8 plus 18,900, that should give you a total of 23,920.8. So now let's add 334.72 TF to both sides. Now for the final step, let's divide both sides by 492.22. So the final temperature of the mixture is 48.6 degrees Celsius. And it makes sense. It's between 15 and 90, any other temperature. Now notice that the temperature change of the water is relatively small compared to the temperature change of iron metal and aluminum. Because water has a very high specific heat capacity, the temperature change associated with water is very small. And notice that we had less water, like the mass of water was significantly less than the mass of the aluminum metal and the iron metal. So since water has a very high specific heat capacity, it can absorb a lot of heat energy without changing its temperature significantly. So substances with a very high specific heat capacity, they will be associated with a small temperature change, whereas metals which have very low specific heat capacities, typically they're associated with a very large temperature change in a heat transfer problem. Let's try this problem. 300 grams of an unknown metal at 200 degrees Celsius was placed in a 50-gram aluminum pot containing 100 grams of water at 21 degrees Celsius. The final temperature of the mixture was 29. What is the specific heat capacity of the metal? So we have another heat transfer situation with three materials. So the unknown metal is at a temperature of 200 degrees Celsius. Now we have an aluminum pot that contains water. But I'm going to draw two separate substances, one for aluminum and the other for water. Now because the water is inside of the aluminum pot, they're at the same temperature, which is 21 degrees Celsius. So heat is going to flow from the unknown metal to the water, and some of the heat is going to flow from the unknown metal to the aluminum pot. So we have three things, but the equation is going to be written a little differently this time. So on the left side, we're going to put the substance that released heat energy, which is the unknown metal. And on the right side, we're going to put the substances that absorbed heat energy, which is the aluminum metal and the water. So it helps to draw a picture so you could see where the energy is going, which substance is releasing the energy and which one is absorbing it. Once you understand that, then you can write the appropriate equation that's going to help you to solve the problem. Now we need to add a negative somewhere. Let's add it to the left side. And now we can solve this problem. So it's going to be negative mc delta T for the unknown metal, and then mc delta T for aluminum metal, and 1 for water. So the mass of the unknown metal is 300. We don't know the heat capacity, we're looking for it. The final temperature of the entire mixture is 29, and the initial temperature of the metal is 200. Now the mass of aluminum metal is 50, the heat capacity is 0.9, and the temperature change, it's final minus initial, so 29 minus 21. And for water, the mass is 100 grams, the heat capacity is 4.184, and the temperature change for the water is the same for that for aluminum. It's the final temperature of 29 minus the initial temperature of 21. So for aluminum, 29 minus 21 is 8 times 0.9 times 50. So that's 360 joules of energy that was absorbed by the aluminum pot. Now in the case of water, it's a temperature change of 8 times 100 times 4.184. That means that water absorbed 3,347.2 joules. Now for the left side, 29 minus 200, that's negative 171. Let's multiply that by negative 300. So this is going to be 51,300 times the specific heat capacity. So now let's add these two values. So 360 plus 3347.2, that's 3707.2. So to solve for C, let's divide both sides by 51,300. So the specific heat capacity of this unknown metal is 0.072 joules per gram per Celsius. "50 milliliters of water at 20 degrees Celsius was mixed with 100 milliliters of water at 90 degrees Celsius. And we know the density of water, it's about 1 gram per milliliter. Determine the final temperature after mixing the two samples of water." So we have a 20-degree sample, and we have a 90-degree sample. If we average the two numbers, if we add 20 and 90 and divide by 2, the average, or the midpoint, is 55 degrees. So here's a question for you. Do you think the final temperature after mixing the two samples of water, is it going to be 55 degrees Celsius? Is it going to be somewhere between 20 and 55? Or between 55 and 90? We know it's somewhere between 20 and 90. Heat is going to flow from the 90-degree sample to the 20-degree sample. And at some point, they're going to reach a final temperature somewhere between 20 and 90. Since the 90-degree sample is losing heat energy, the temperature of that sample is going to decrease. And since the 20-degree sample is gaining heat energy, it's going to increase. The question is, where is the final temperature? Now we have 50 milliliters of the 20-degree sample and 100 milliliters of the 90-degree sample. If these two values were the same, then the final temperature would be right in the middle. It would be 55. But since they're not the same, it's not going to be at 55. Since we have more of the 90-degree sample, the final temperature should be somewhere between 55 and 90. So let's see what it's going to be. So since we only have two samples, this is the equation that we need. QA is equal to negative QB. So MC delta T is equal to negative MC delta T. So let's say the left side is for the cold water sample and the right side is for the hot water sample. Now the density of water is 1 gram per milliliter. So if you multiply the volume by 1 gram per milliliter, you'll get the mass. So 50 milliliters is equal to 50 grams of water. And 100 milliliters is 100 grams of water. So the mass of the cold water sample is 50 grams. Now the heat capacity, or the specific heat capacity for water, is the same. So we could divide both sides by C, and those two units will cancel. The final temperature of the cold water solution, we're looking for that. So let's call that TF. The initial temperature is 20, and then minus 100 times the final temperature of, well, we're looking for that too. The initial temperature is 90. So to simplify this equation, let's divide both sides by 50. So these two will cancel, and we no longer need the parentheses on the left side. So on the left is simply TF minus 20. On the right side, 100 divided by 100 divided by 50 is 2. So let's distribute the negative 2 on the right side. So it's going to be TF minus 20 is equal to negative 2TF. Negative 2 times negative 90, that's positive 180. So to solve for TF, let's add 2TF to both sides. And simultaneously, let's add 20 to both sides. TF, or 1TF plus 2TF, is equal to 3TF. 180 plus 20 is 200. So let's divide both sides by 3. So the final temperature is 200 divided by 3, which is 66.7 degrees Celsius, which is between 55 and 90, as we predicted. So that's how you can calculate the final temperature after mixing two samples of water at different temperatures. Let's try this problem. 30 grams of sodium hydroxide was dissolved in enough water to produce a 125 milliliter solution. The temperature increased from 22 to 79 degrees Celsius. We have the density and the specific heat capacity. What is the enthalpy change for the dissolution of NaOH? So the dissolution of sodium hydroxide, is it endothermic or is it exothermic? What would you say? The answer is exothermic. The temperature of the solution increased from 22 to 79. But when the temperature goes up, isn't that an endothermic process? Doesn't that mean heat is absorbed for the temperature to go up? And yes, that is true, but you need to know what is the system and what is the surroundings. The reaction is the system. When sodium hydroxide dissolves into Na plus and OH minus ions, it releases heat. Right now, initially, the temperature of the water is 22. But as sodium hydroxide dissolves into ions, it's going to release heat to the surrounding water molecules. So the dissolution of sodium hydroxide is an exothermic process. So let's say the reaction is the system. So sodium hydroxide loses energy as it breaks up into ions. As it releases energy, water, which is the surroundings, it absorbed that energy. So the temperature of the water goes up from 22 to 79. So for H2O, the process is endothermic. But the reaction, the dissolution of NaOH, is exothermic. So make sure you see the difference between the two. So if you have a problem where a reaction is taking place within water. If the temperature of the water goes up, it's endothermic for the water, but the reaction that caused that event is exothermic because it's releasing energy to the water molecules. Likewise, let's say if you put another salt in water, and if the temperature of the water decreased, that means the surrounding water molecules lost energy. So it's exothermic for the water, but the reaction absorbs energy from the surrounding water molecules, so it's endothermic for the reaction. So if the temperature of the solution goes up, the reaction is exothermic. If the temperature of the solution goes down, the reaction is endothermic. Now let's talk about how we can solve this particular problem, how we could find the enthalpy change. If you want to find the enthalpy change of the reaction, it's going to be Q divided by N. Usually the units of delta H is in kilojoules per mole. Now we could find Q using this equation, Q equals MCAT. But you need to be careful though. This is Q of the reaction. Q of the reaction is equal to negative Q of water. So let's say if water absorbs 1,000 joules of heat energy, that means the reaction releases 1,000 joules of heat energy. N is the moles associated with sodium hydroxide, which is for the reaction. So first we got to find Q of water. Using that, we can calculate Q of the reaction, which is going to be in joules. We'll have to convert that to kilojoules. And then we'll divide the Q of the reaction in kilojoules by the moles, and that should give us the kilojoules per mole for this reaction. So let's begin. So let's find out how much energy water absorbs using the equation Q equals mc delta T. So what is the mass of the water, or the mass of the solution? For the most part, the solution is made mostly of water. So the water molecules are absorbing most of the energy. So the mass of the solution can be found by multiplying the density of the solution by the volume of the solution. So notice that the units, milliliters, cancel. So it's 1.08 times 125. So the mass of the solution is about 135 grams. So instead of saying Q of water, let's say Q of the solution. That's 135 grams times the specific heat capacity of 4.18 multiplied by the temperature change. Final minus initial, 79 minus 22. So 79 minus 22 is 57 times 4.18 times 135. So the solution absorbs 32,165 joules of energy. Now let's convert it to kilojoules. If we divide it by 1,000, that's 32,000.165 kilojoules. So if the solution absorbs that many kilojoules of heat energy, the reaction releases an equal amount of heat energy. So Q of reaction is negative 32.165 kilojoules. So now that we have that, let's calculate the moles of sodium hydroxide. So we have 30 grams of NaOH, and to convert grams to moles, we need to use the molar mass found in a periodic table. So the atomic mass of sodium is about 23. For oxygen is 16, and the atomic mass of hydrogen is 1. 23 plus 16 plus 1 is 40. So the units for the molar mass is 40 grams per mole. That means that 1 mole of sodium hydroxide has a mass of 40 grams. So if 40 grams corresponds to 1 mole, then 30 grams is how many moles? So if we divide 30 by 40, we're going to get 0.75. So 30 grams of sodium hydroxide corresponds to 0.75 moles of NaOH. So now that we have the moles of sodium hydroxide, we can now estimate the enthalpy change for the reaction. So it's Q divided by N. So it's going to be negative 32.165 kilojoules divided by 0.75 moles. And that's equal to negative 42.89 kilojoules per mole. So that's how you can estimate the enthalpy change for the whole reaction, or the dissolution of sodium hydroxide, in this particular problem. Let's try this one. 18 grams of calcium chloride was dissolved in 150 grams of water at 20 degrees Celsius. The specific heat capacity of the solution is 4.18. What is the final temperature of the mixture? So we have a thermochemical equation. That is an equation that is associated with an enthalpy value. Now what you need to know is that if 1 mole of calcium chloride is dissolved, negative 81.5 kilojoules will be released. If 2 moles of chloride is dissolved, negative 81.5 kilojoules of heat energy will be released. So 2 moles corresponds to this energy value, and 1 mole of calcium chloride corresponds to this value. So what you have is a kilojoule per mole ratio. And that's what you need to understand when you have a thermochemical equation. So we know that 1 mole of calcium chloride will generate 81.5 kilojoules of heat energy. So knowing that, we can calculate the Q of the reaction using conversions. Let's start with 18 grams of calcium chloride, and let's convert it to moles. So we need to find the molar mass. The molar mass for calcium is 40, and for chlorine it's 35.45, but we need to multiply that by 2. 35.45 times 2 is 70.9, plus 40, that gives us a value of 110.9. So 1 mole of calcium chloride has a mass of 110.9 grams. So let's set it up in such a way that the unit grams cancels. Now let's convert moles into kilojoules. 1 mole of calcium chloride is going to release negative 81.5 kilojoules of heat energy. Now, since the specific heat capacity is in joules, let's convert kilojoules into joules. So 1 kilojoule is equal to 1,000 joules. So these units cancel, and these as well. So 18 divided by 110.9 times 81.5 times 1,000 gives you a value of negative 13,228 joules. Now this is the Q for the reaction. That's the dissolution of calcium chloride. So therefore, the Q for the solution must be positive. If the reaction is exothermic, then the solution must be endothermic. It has to absorb the energy. So it's positive 13,228 joules. So now we can use this equation to calculate the final temperature of the mixture. So Q is 13,228. The mass of the solution is the sum of the solute and the solvent, so it's 168. The specific heat capacity is 4.18. We're looking for the final temperature, and the initial temperature is 20. So let's multiply 168 by 4.18. and you should get 702.24. Next, let's divide both sides by 702.24. So 13,228 divided by 702.24, that's equal to 18.84. So the last thing we need to do is add 20 to both sides. So the final temperature is 18.84 plus 20. So that's 38.84 degrees Celsius. So that is it for this video. Thanks for watching and have a great day.